Hello everyone, I'm Aaron Larson, Associate Editor of Power Magazine, and I want to welcome you to our webcast titled 20% Incremental Capacity in 60 Seconds, Turbophase Installation Case Study. Today's program is sponsored by Powerphase and hosted by Power Magazine. During the session, attendees can expect to learn how a fast-responding modular gas turbine turbocharger is being used to boost capacity, energy, and regulation revenue at a combined cycle power plant located near Chicago. The presentation will provide details about the installation and lessons that have been learned. Attendees will also learn about the testing procedure and third-party engineering analysis that has been completed. You will gain an understanding of performance expectations for F-class machines and details on the output gained by injecting 2 modules into 1 gas turbine. Bob Kraft, President and CEO of Powerphase, and Bruce Kelly, Plant Operations Services Manager for Sega Incorporated, will give the presentation. Mr. Kraft spent 15 years in advanced aircraft engine engineering at GE and Pratt & Whitney prior to co-founding Power Systems Manufacturing in 1998. Among PSM's first products was a cutting-edge ultra-low NOx combustion system for retrofit onto GE and Westinghouse gas turbines that reduced NOx emissions from 25 parts per million to less than 5 ppm. After Calpine acquired the company in late 2000, Bob remained as the Vice President of Engineering, and in 2008 he became President after Alstom acquired the company. Under his technical and business leadership, PSM became the world's leading alternate source supplier of advanced components for the state-of-the-art F-class fleet of industrial gas turbines. In 2011, Bob founded Powerphase, which has developed the Turbophase air injection system as a smarter way to add more natural gas generation to the power grid. Mr. Kelly has 35 years of consulting experience in the power industry covering performance, optimization, simulation, and equipment condition monitoring for fossil-fueled power plants. Bruce has been to the Turbophase installation and performed analysis based on the raw data files. The presentation will last about 30 minutes and will be followed by a question and answer period. Before we get started, I would like to run through a few housekeeping items. At the lower left-hand side of your screen, there is an area where you can type and submit questions to the speaker. Feel free to send in questions at any time during the presentation. At the end of the program, we will answer as many questions as possible. If you are experiencing any technical difficulty, you can type the problem in the same area on the lower left of your screen, and a member of our production staff will assist you. This program is not available for download. However, it will be archived on our server, and future viewing will remain free of charge. You can use the same URL to reach the archive program as you did to reach the live program. A certificate of completion for professional development hours will be sent out via email to every registered participant who attends. Before we begin, I would like to thank Powerphase for underwriting today's program. Their generosity allows everyone to attend the presentation at no cost. With that, I'll turn the program over to Bob.
Good morning. This is Bob Kraft, the founder of Powerphase LLC. I want to acknowledge Steve Quisenberry, who's our Vice President of Sales here at Powerphase, for helping put this presentation together. On the first chart, you see a picture in the right side of our Turbophase module at the Morris Cogen facility. And on the left-hand side, you see actually a picture inside that module of the natural gas reciprocating engine that drives our process. Chart 2 is a fundamental relationship between power output and ambient temperature at a typical gas turbine power plant. And many people recognize that the airflow through the gas turbine and consequently the fuel and power output of gas turbine reduce significantly with increased ambient temperatures. And also, many gas turbines have system that preheats the inlet, typically called an inlet bleed heat system, on very cold days. And very cold days and very hot days are when typically you need the power most. And the Turbophase system literally just replaces the missing air. So we restore that air and restore a constant amount of power over the whole ambient temperature range. And I'm going to show you here in this presentation some data where we were able to achieve a 20% power boost on a 6B gas turbine in 60 seconds. And the interesting thing about our process, and I'll get a little more in detail about it, is that it's extremely efficient. So more efficient than chillers, independent of the ambient conditions. So it's a very unique product that isn't out in the market today until this product existed. And the system is extremely fast, and we're working right now to make it qualify for the high-speed regulation market in markets like the PJM market in the Northeast U.S., where they'll pay 2 to 3 times the dollars for the same regulation because it's faster. So this system is extremely fast, and it's going to bring new revenue streams to a plant that they previously didn't have access to before. So on chart 3, the Turbophase system simply adds that missing air back into the gas turbine. And in the upper left-hand corner of the picture, the 3 blue boxes represent the reciprocating engine that's driving our high-efficiency compressor, and that's an intercooled compression process, so it uses quite a bit less horsepower to pump the same pressure air compared to the gas turbine, and that's one of the sources of efficiency of our system. And then we take the waste heat from the reciprocating engine, the exhaust, and run it through a heat exchanger. So that's a 100% stainless steel system that heats up that air that's coming out of the compressor. And lo and behold, we have this air that comes out of our system that looks pretty much exactly like the air that's coming out of the gas turbine compressor. And we just simply add that typically in the compressor discharge wrapper, which is upstream of the combustion system. And so our air flows into the combustor and through the turbine. And when it flows through the turbine, for example, when we put in 5% more air into that combustor, we make 5% more power out of the turbine, and we increase the exhaust flow 5%. But what's interesting is, since our separate compression process is generating this airflow, the gas turbine compressor really doesn't consume much more power, and all 5% of the turbine power goes to the gas turbine generator, which is shown here as a cold end drive, like on an F-class type machine, and it turns out to be about a 10% power increase. And so when we add 5% more air to the gas turbine, we get 10% more power out of the generator. It also increases the HRSG output steam production by about 5%. And one of the byproducts of our process also with this extra turbine flow is a higher pressure drop and consequently a higher temperature drop. So our exhaust flow is slightly cooler, which actually adds about 7% more duct burning capacity. So basically we can add 10% more power to the gas turbine, and there's 10% more power, more than 10% more power available to the steam turbine if you want to duct fire your duct burners harder. So flipping to chart 4, our first commercial installation was complete this summer at the Morris Cogen plant, which is in the PJM market. It consisted of 2 Turbophase modules, and these modules are, and I'll show you in a later slide, they're delivered pretty much complete and pre-tested, so they install very rapidly. I'll show you a quick video in a second on that. Typically 2 to 3 days, and the second one we install in 3 days, single shift operation. And in 2012, this was a concept. You see the diagram on the left there. In 2013, we had our first system at the PowerGen in Orlando in November 2013. And in January 2017, we sold our first one to this Morris Cogen facility. So I'm just going to run a quick time-lapse video take about 15 seconds to show you the installation of the second module at the Atlantic Power Site. So that was the second module being installed at the Morris Cogen. As I mentioned, it took 3 days to install it, and we believe we could put a 50 megawatt system on a 7FA 2-on-1 plant, which is one of our, I'll call it a typical installation that we're targeting in a couple days. And all the preparatory work gets done ahead of time, and you can see at the bottom of chart 4 there, basically a month after they signed the contract, they went for the permit, which took them about 14 weeks to get. And I'll talk a little bit more about that later. And for a few months, the site preparation work was underway. We're basically doing the foundation design and installation, the air injection piping, the little bit of electrical that we consume, maybe 35 kilowatts, and the controls work, and which is basically run on a couple wires. And on June 15th, our second Turbophase module showed up, and on June 18th, we were running the system and injecting into the gas turbine. And on the 25th, we had our first performance validation testing where we demonstrated the 20% power boost. So on slide 5, the module, this is a kind of diagram of the module and all the different components. And I'm not going to go through every component, but let me just say that everything that you see in this picture is part of our price for our system. When we sell a system, it's a complete package, pre-tested in a nice sound and weather enclosure, and it's ready to plug into the plant in very rapidly with just a few hookups. So on chart 6 shows an overview of the gas turbine power plant, the Morris Cogen. You see the 3 gas turbines on the right. There's 6 speed gas turbines. And the red lines are the air pipes connecting the gas turbines to the 2 Turbophase modules, which you see on the left-hand side, Tpm 1 and 2. And what's interesting is they have a chiller system at this plant, and we actually operated our system alongside with the chiller at full power, as well as duct firing at full power and peak firing at full power, and our system worked flawlessly. So we basically have an 8-inch header that comes from the Turbophase modules and runs across that plant rack piping, the vertical red line, and then we have 6-inch pipes that feed each gas turbine. And you can tell with this diagram, we can actually put air into any one or a combination of the gas turbines, so it's a system that can be used at the whole plant. It's not tied necessarily to one gas turbine. And then the green and orange lines are the water supply, the green lines, and the blue, the water return. And just for reference, this system, it can use a multitude of different types of cooling schemes, and this system, 2 Turbophase modules at this plant, consumes about 1% of the plant cooling capacity. So slide 7 shows the actual connection into the gas turbine, and we did this whole installation without taking a plant shutdown. So what we did is in the bottom left-hand corner of that diagram off the page, there's a manual isolation valve for the inlet bleed heat system. And that inlet bleed heat system works perfectly for an air injection system. It's designed to bleed about 5% of air out of the gas turbine, and we use it to pump 5% air into the gas turbine. And typically they have a manifold inside the turbine cab that distributes the air to the gas turbine. And so we didn't have to go inside the cab at all. And once we keyed in this pipe and put the cap on it, and actually we put a valve on it at the right-hand side of our air injection T, and the system's basically ready to be installed, and the plant can operate as normal. So again, we installed all these two modules, all the air piping, the cooling system, and so forth, without taking a plant shutdown. So I mentioned the permit earlier. It took 14 weeks to get the permit, and the basic premise is that our Turbophase system is extremely more efficient, 30 to 50% more efficient than duct burners, and that means less fuel and less emissions. So when you look at how you typically operate the plant with our Turbophase system, you're actually going to produce less emissions out of the plant on an annual basis, and that's basically what they put to the permitting agency, and then in return they got the permit in 14 weeks. And the interesting thing I thought was that there's actually no testing. There was no testing required. Only if they request a test, we have to produce test results in 90 days. And that permit's available. It's a publicly available document if you want to see the whole thing. So slide 9 is the controls integration to the plant. And a gas turbine at base load already knows what to do with more or less air. And we really don't have to touch the control system. So you put air in, it adds more fuel. You take air out, it adds less fuel, maintaining firing temperature. And we put in controls into the plant DCS system to allow the operators to remote control this and also to run it on AGC. So the Turbophase control systems consists of basically a megawatt input to our Turbophase module, and that basically translates to an airflow out of our system. So our system knows when it gets a megawatt signal how much air to pump, and it turns on the appropriate number of Turbophase modules in 60 seconds and pumps that air. The gas turbine controls are completely unaffected, and we have a number of safety and operation parameters ported to the plant control system, including a hardwire e-stop. And so a typical, if you're looking at the power plant and you're in the control room, we'll have a Turbophase health monitoring system that's just like any other system. It shows you, it starts flashing at you if it sees something that's a little bit out of whack. So it gives you a warning if something's going on. And then on the plant side, on the same DCS system, we kind of show where the air is going to which gas turbine and how much incremental power is coming from the system. So chart 10 is actual data. And the reason the lines look really fuzzy is because it was 1 second data, and the megawatt meter at the plant bounces around a little bit. So one of the unique things about our system is it's, as I mentioned in the beginning, we pump the same amount of air independent of ambient conditions. So our test, this is actually a profile. The first 3 bumps are the gas turbine going from 31 megawatts. So if you're looking at the orange line, it goes from 31 megawatts up to 34 megawatts and back down to 31. And we basically had a hold time there for 20 or 30 minutes. And we just do that 3 times. We average the before and after results, and that's the megawatt increase. And the fuel increases, just measuring the gas turbine fuel flow and the incremental fuel flow to our Turbophase modules. And then on the very right-hand side there, you see we brought up that first Turbophase module again. We got the incremental 3 megawatts, and then we turned the second Turbophase module on and got the second 3 megawatts. So there's 6 megawatts on a 31 megawatt machine is just about 20%. And this was tested, these test results was at an 85-degree day. And when it's 95 degree, the plant outputs less than 30 megawatts, so it would be a little more than 20%. But also on the very right-hand corner, you see there it says Tpm Air Compressor Trip. As I mentioned, we took this data pretty much immediately after we installed the system, and we were having a little issue with the plant instrument air, which we've resolved. But at the time, we rented an air compressor to give our valves instrument air, and it ran out of fuel while we're testing. So while part of our test plan was actually test what happens if a Turbophase module trips, we actually tested it unbeknownst and unplanned, and basically the gas turbine just dropped down to, one Turbophase module. So we were injecting and getting 20% more power out of the gas turbine, and we dropped down to 10% in about 2 seconds. So, and all the gas turbine parameters are fine. So when we look at the results of the Turbophase module, and I apologize, chart 11 is a little bit busy. We measured both what we call Tpm 1 and Tpm 2 measured results, and the majority of the power comes from the gas turbine. So you see 2.72 and 2.76 for Tpm 1 and 2 from the gas turbine power, and then the steam turbine 0.32 megawatts, for a total of between 3.04 and 3.07 megawatts, where we predicted 3.06. So it's actually extremely simple and straightforward to predict the power output of the gas turbine with incremental airflow. And we had a third-party engineering company, Sigma, not to be confused with Sega, but Sigma, do an engineering report looking at this. They actually witnessed this testing, and they came up with numbers that were slightly more favorable in megawatts. And one of the unique things we didn't really anticipate when we ran the test, but we should have in hindsight, it's pretty clear, is the gas turbine fuel meter. We're looking for 10 MMBTUs of fuel increase to the gas turbine on a meter that's reading 350 MMBTUs. So the tolerance, the 0.25% tolerance on the fuel meter was plus or minus 700 points in incremental heat rate. So all the numbers that we came up with, all the numbers we measured, all the numbers that the independent third-party analyzed are all well within that band. And it's just kind of a matter of how you slice the data, because it bounces around a lot, because the fuel meters they bounce around a little bit. So moving to chart 12, I mentioned we had that rapid trip test. This is actually the power. So we're at 33 megawatts. You see the blue line. And in 2 seconds, we lost the power down to 31 megawatts. So or 30.7 megawatts. So we lose the power immediately. And the red line is just one of the gas turbine control parameters we looked at, which is exhaust temperature. And when you put less air into the gas turbine, your turbine exit temperature goes up, and it basically jumped right up where it should be and leveled out. So a typical gas turbine control system is updated every 10 milliseconds. So it's trying to move and adjust the gas turbine based on measured parameters in the gas turbine every 10 milliseconds or 100 times a second. But realistically, when I talk to the controls guys, the best thing that's really going on out there is about once every or 10 times a second or every 100 milliseconds there's actually a movement. So a 2-second trip event, which seems awfully fast to us, the gas turbine valves are moving 20 times in that 2 seconds. So the gas turbine has no problem keeping up with something like that. And actually, if we do lose a Turbophase module like we did here, the combustion process, which would potentially give you problems, is more stable when you lose air momentarily. So it's a rich event which stabilizes the combustion process. So we weren't predicting any issues. We tested it a couple different times, both planned and unplanned, and there's no problems. Chart 13 shows the actual compressor surge, which is one of the parameters that we watch when we're injecting air. Basically, there's 3 things that'll limit how much air you can put in a gas turbine, and that's the compressor stall margin or surge limit, which is plotted here, generator limits or other electrical limits at the facility, and the shaft limit of the physical shaft torque on the gas turbine. And when we look at that for the 6B on that 80-degree day that we were testing, you see this plot is a plot of the compressor discharge pressure on the left versus ambient temperature, and those orange blocks at 145 psi compressor discharge pressure are before injection, and then the triangles above on the right, the two sets of triangles on the right, are with one turbophase module, and the 82.5 degree data, the single block with the jump up higher triangle, is the two modules. And that blue curve, what we're calling the limit, is something that can be pulled out of the control system, which actually has margin on the actual surge of the gas turbine. So you can see here, even with two modules, we're still significant distance away from the surge limit. And when we looked at the generator and shaft limits, it basically said we could actually put 25% more air into this gas turbine and get 50% more power out of it before we hit a physical limit at the plant on an 80-degree day. So even the 10% more air with 20% power is woefully conservative compared to what the gas turbine is capable of doing. So, at the end of the day, it's all about economics. And one of the things we've done is we've worked with a company called Energy Exemplar, and they actually wrote the code for that ERCOT uses to dispatch gas turbines in the ERCOT market. And I apologize, we don't have one here for the PJM. We're working on it. But this is a typical, the result of their work. And it shows if you had a Turbophase module at a nodal location in the PJM market, and we have a power plant that this represents, they would have a net increase in profit of $5.2 million per year with a 2.5% air injection system. So basically, it was 5 Turbophase modules at a 2-on-1 7FA, and 5 Turbophase modules represents 5% injection in one gas turbine, or 2.5% in 2 gas turbines. And so they ran this analysis for us and for the customer, and with a 13 megawatt increase and a $5.2 million increase in profit, our pricing basically, this comes out to be about a 2.5-year payback, or 2-year payback. So this analysis includes, the actual nodal gas pricing, the nodal power pricing, and the dispatch changes based on the heat rate changes. And I didn't really go into that, but when we put it on a combined cycle plant, our production system now basically is heat rate neutral on a combined cycle plant, and a 2 to 3% efficiency improvement or plant heat rate improvement on a combined cycle plant. So with that concludes my presentation, and I just want to reintroduce Bruce Kelly, who's one of the principal engineers at Sega, who is an engineering party that has come out to witness our Turbophase system at the Morris Power Plant. Bruce?
Good morning. Thanks, Bob, and hello, everybody. My name is Bruce Kelly. Sega Incorporated is an engineering firm in Kansas City, and we're pretty focused on steam and electric generation applications. And I was interested in this technology because I thought it would be really great if you could increase the capacity of a compressor without having to put other stuff on there in front of it, whether it be inlet fogging or chilling, or whether you had steam injection. If you could do it and make it seem like the compressor was just bigger, wouldn't that be great? So I had the opportunity on the 30th of June, while they were still in testing, to visit the facility. And I was not there to be a witness specifically for Powerphase, but I was interested in my position as a performance engineer. I was interested in having a look at this technology from the perspective of our clients. So it was really great to have that opportunity. I thought I would just give you a little rundown on what I saw, try to keep it pretty factual. When we got to the plant on the 30th, we had complete access to the whole system. We got to walk down the unit, the picture that Bob put back up, all the piping, all the wiring, got to poke our heads inside the unit, climb around on top of the engine, and really get a good look at this technology, which is very interesting and significant in my opinion. Then we got to see it start up. I was standing right next to the unit. In fact, if someone could advance to the last slide, there's a picture of the unit that was, or I can do it. There we go. The Unit 1, Unit 2 was still being installed when I was there. Unit 1, I stood right next to that door as they started the unit up, and it sounded like a diesel engine starting up, and then we closed the door and the sound went away, and we got to stay out there while they went through the speed ramp up to full speed with no load, and then go back to the control room and watch them load the unit up. And since they were still in testing mode, it took about 20 minutes to go from 0% valve to 100% valve. But over the course of that time, I got to watch the power increase at a squared curve, which you'd expect as the valve opened. And my witness on it was we saw a 2.6 megawatt increase in that 20 minutes as they went from 0% to 100% turbophase air. And then they took the air back out, and we lost the 2.6 megawatts. And I think in testing they got a little bit more, but on that particular day, that's what I saw. So my interest was to see whether or not it would work, and which it just made sense that it would, and they gave us access to look at it and witness that it did work. So it's basically all that I had to add to it was that I got a chance to see it. It did work, and I'm very interested to see how it would behave on a larger unit. And so I'll just pass it back to you, Bob.
Thanks, Bruce. So
if you don't have any additional, we'll go on to the question and answer session. And thank you for your presentation, both Bob and Bruce. We've had a large number of questions come in from the audience during the course of the program, and we'll try to consolidate similar questions and answer as many as possible. And if we don't get to some of the questions, we will be responding via email to those that we may not be able to answer during the webinar. But to begin, we have a question from an attendee that says, on a 7FA machine rated at about 171 megawatts at ISO, what would be the expected megawatt gain?
I think it's extremely safe for the 7FA to be about the 25 megawatts. And really there, what we'll be limited by is the electrical limits of the plant. So, between 22 and 25 megawatts is a very safe number. We've actually done some testing early on that would suggest that we could basically get maybe 50% more than that in the 30 to 35 megawatt range. But again, it'll be limited by the electrical plant capacity.
All right. Thanks, Bob. Another question, does your simple cycle heat rate calculation include the fuel for the air compressors?
Yeah. When we talk about an incremental heat rate, our modules burn about 16 million BTUs per hour of fuel. And on this 6B gas turbine, it burns about an incremental 10 million BTUs of fuel. So a total of 26 million BTUs of fuel per hour. And if you divide that by the incremental power, you'll come up with our heat rate numbers. So that includes both the Turbophase module and the gas turbine incremental fuel.
All right. Another question about cooling water. How much cooling water is required per unit?
The system, it's set up for 600 gallons per minute. It's a closed-loop system. You'll notice there's, well, maybe you can't tell from the picture, but there's no radiator in the system. So water comes in a 6-inch pipe, 600 gallons per minute. It runs through the compressor intercoolers, through our lube oil system cooler, through our engine high and low temperature cooler, and then back out a pipe right next to the other 6-inch inlet is a 6-inch outlet. So one pipe in and one pipe out, and the cooling's done. And we've done that because we can integrate this system into the combined cycle plant, where we can basically put our waste heat into the condensate heat-up process. It's kind of like an economizer for the plant. But in this case, we just did a very simple. We just took water from the cooling tower and circulated it through. And as I mentioned in the presentation, it represents about a 1% cooling load. And we've looked at some systems that are, say, air-cooled power plants, where the steam turbine back pressure starts to come to play in the high temperature output of the plant, where the steam turbine power starts to drop off quickly. And what we found is, the gas turbine itself uses a fraction of the cooling compared to the steam cycle. So since our augmentation is really gas turbine eccentric, it's not like a duct burner that's steam turbine eccentric. We can add a typical, 50 megawatt system on an air-cooled 2-on-1 7FA, where they might start running into problems on their ACC on 100 degree or hotter days. Our system, the incremental power boost at those temperatures, 100 degrees and hotter, might drop from 50 megawatts to 45 megawatts, for example. And your gas turbine, or your steam turbine is losing power, but you're gaining it, a factor of 10 faster on the gas turbine. So it's really, really a good product to boost the power on really hot days.
Okay. And I think you may have kind of touched on this during your presentation, but a question came in about why and how did the TPM2 air compressor trip?
Well, our production module has its own instrument air system, and the Turbophase module itself actually didn't trip. It was we had rented a small diesel air compressor to feed our instrument air system while we got it hooked up at the plant properly, and it ran out of fuel. So during the testing, that data I showed you, where we had 2 Turbophase modules pumping into one gas turbine and making 20% more power, we lost the air to one of actually it was Turbophase module number 2, and when that happened, the power and airflow fell off. The Turbophase module was still running, but it was just dumping all the air to atmosphere, because I mentioned our fail-safe control system. Well, when you lose instrument air, just like a gas turbine power plant, if you lose instrument air at the gas turbine power plant, it shuts down. And the same thing is true with our Turbophase module. If you lose instrument air, it fails safe and dumps all the air that's being generated by the Turbophase module to the atmosphere through a silencer, which is also used for the startup process of the Turbophase module. But it dumps all that air to atmosphere instead of the gas turbine. So the module itself was still pumping air. It just wasn't going to the gas turbine because we lost fuel to our portable air compressor during the test.
Another question about air: is the extra air provided to the by the Turbophase module filtered?
Yes. Yeah, we have. We could put any type of filtration system on the thing, and we have HEPA filters on this, basically filtering it to the same level that the air to the gas turbine is being filtered. And one interesting thing about these compressors is they're used commercially for a lot of different processes that require oil-free air. And one of them, for example, is on snowmaking. So if you go to a resort in Colorado, they might have 15 or 20 of these type of compressors. Typically run with electric motors, but it's oil-free air. So our air is super dry because it actually, the intercooling process takes the water out of it, and it's oil-free. So it's a very clean, filtered air.
All right. Another question here about Turbophase. So Turbophase comes in one size, and you buy as many as needed based on the size and quantity of gas turbines served. Sounds like 5 Turbophase units needed for a single 7 FA. Can you speak to that?
Yeah, that's true. We're making a production, I call it a production blue box. It's 8 feet wide and 32 feet long, and it's a production system, and it works on literally every gas turbine in the world, 20 megawatts and higher. And yeah, for a 20 megawatt machine, you use one module. For a 7FA type machine, you use 5 modules. And what that does for you is, and you'd be surprised how small the footprint is. I mean, if you look at the aerial view of the plant, that's 20% more power, taking up probably 2% more space at the plant. So it's a very space-conscious piece of equipment, even with 5 modules per gas turbine. And it doesn't have to be located next to the gas turbine either. We're working with customers where it's going to be basically a half a mile away. So, but anyways, you have to have multiple units on these bigger gas turbines. But what that does is it gives you a much higher reliability factor. So, we did some reliability analysis, and we're working on some more detailed analysis on that. And say you have a 2-on-1 7FA, and you got 10 modules sitting there. And I didn't talk about, we have a little peak button on our module, so it'll let you put 10% more airflow out. So if one happens to go down, you still can get the output from 10. It's not like an all or nothing. And then you can spread it across any gas turbine in your power plant. So it really helps the reliability part.
All right. Another attendee was interested in a Sigma report. Do you have a Sigma report available?
Sure. If anyone wants a Sigma report, they just send us an email, and we'll send it to them.
Okay. Another one. Do you have endorsement from General Electric on any of the LM model of engines, such as the LM 6000, 2500, or LMS 100?
Well, if you know my background, I started Power Systems Manufacturing, which is the largest OEM alternative to all the spare parts for all these large and medium frame gas turbines. And so General Electric and others really, I'll say, don't like what we're doing in that business, and for a different reason, don't necessarily like what we're doing in this business, because we're basically displacing, potential gas turbine sales. And so I wouldn't anticipate that we're ever going to get an endorsement from any OEM, but we have had literally dozens of customers go to the OEMs, and when I say the OEMs, every one of the large OEMs that make gas turbines, and ask them anywhere from, guys that have long-term service agreements to guys that just buy on a parts basis, on a transactional basis, ask the OEMs that question, and we're still moving forward with all those customers. So I think we're getting a very favorable response, and part of the reason is because the OEMs advertise that all of their gas turbines are designed for 5% injection. And Siemens Westinghouse would actually have a bigger number than that. And if you have an older frame machine, there's publications from General Electric that are all up to 9% injection. And, it was originally intended for steam injection. That's what they really meant when they talked about injection, because no one really had come up with a really cost-effective air injection product. But there really is no difference between steam injection and air injection, except the obvious that when you put more air in the gas turbine, there really is, it's just like it got a little cooler outside, and the gas turbine naturally picks up the extra power. So I'm pretty confident if the customers talk to the OEM, they're going to get a pretty favorable response, but I doubt we'll ever get a endorsement.
All right. Another question about your fuel choice. Why not use natural gas engine drive instead of diesel?
Okay, so the picture of the presentation that we just did at the Morris plant is natural gas. It's a 2 megawatt natural gas machine, and that same 2 megawatt box works on every gas turbine and makes, at this power plant, a little over 3 megawatts on the gas turbine, and on a 7FA makes over 5 megawatts on the gas turbine. So this module is natural gas. We do have a diesel system that's in Saudi Arabia, and we're selling both systems right now. And another interesting thing is these engines are designed to, I'll probably oversimplify here a little bit, but pretty much burn anything. So, any type of biofuels or landfill gas, things like that, you can convert into a lot more power at the power plant than you can just running a recip at the at the source of the biofuel. And not only does it make more power, but it's a lot more efficient. So, the most efficient recip are typically in the mid-40% thermal efficient. And on a 7FA or a 501F, if you were using some type of gas to burn our system, it's well over 50% thermal efficient. So it's the same as basically as the combined cycle power plant.
Another question about injected air. Is the injected air temperature held at a constant? And if so, what is that temperature?
Yeah, it's held at a constant, and it's a function of that silver box on top of the module. It's what we call the recuperator, and typically we target to be hotter than 500 degrees Fahrenheit because that's typically what the OEMs are expecting to be injected into a gas turbine from steam, for example. But at this plant, our injection temperature was about 570 Fahrenheit, where the compressor discharge was like 650. On a 7FA, where things are maybe 100 degrees hotter, we would bump our temperature up into the 650 range. And yes, it is pretty much constant. It might fluctuate 5 or 10 degrees Fahrenheit, but it's pretty constant.
Okay. Are the units in service all operating in peak service, or have they been continuously operated, such as any issue with base loading the system?
Well, the natural gas engines specifically are really going after a base load market. So, these engines, it's unique. Compared to a gas turbine, they don't count starts on the recip engine. So you can start and stop it as many times as you want. It's kind of like your car. Just the mileage. It's not how many times you start and stop it that you have to do the maintenance. But this unit is really geared for making the plant a lot more responsive to the grid signal. So we're anticipating that 80% of the year it's used in a very fast-acting regulation market, and then when they hit the really hot days, used for base load power.
Okay. What about the power consumption? What's the power consumption of both packages?
So I believe it's about 35 kilowatts per module. It's on that order, and it's a 480 three-phase. That it's basically we're talking about ventilation fans and a couple pumps pumps that are pumping the coolant through the module is really all the load that's being consumed while you're running. There is a ancillary load when the system's not running. When you want to get it ready to start, there's basically engine heater blocks and lube oil for the compressor heating elements that also are under the 35 kilowatt range. And depending on what temperature on it, it's a variable on how long it takes to heat up. But I should mention too that part of our product, we have a lot of technology wrapped around how we actually inject the air. So we have a process that basically keeps the air pipe between the gas turbine and our Turbophase module hot all the time. So when the plant's on a regulation, has been in regulation, and it needs to be able to start fast, literally the whole system, you just hit one button in the control system, a ready to start button, and we preheat the air pipe and our Turbophase module. And we have a couple different ways to do that. So it's basically ready to start in 60 seconds.
Okay. What is the effect on combustion dynamics for both diffusive and DLN combustion systems?
Okay, so you heard a little bit about my bio. We've built pretty much all the popular frame combustors in my previous company, Power Systems Manufacturing, so I'm half a combustion expert. And so you can maybe believe me when I tell you that actually when we add more air to the combustor, we're actually improving every element of what you would look for in combustion stability, which in turn is dynamics. So we add, on a really hot day, the combustor's really off design and really is looking for more fuel and more air. That's what we do. So we push the combustor towards more fuel, more air, more stable process. And this combustion system was a DLN1 style system, and it didn't have combustion dynamics on it, so we couldn't measure it here. But I was involved with my last company doing an air injection testing on a 7FA with a DLN 2.6 combustion system, and we did measure the combustion dynamics there. And both the combustion dynamics and the emissions improved, just out in the second or third decimal place, just a little bit, but in the direction you would expect it to go. And so everything we're doing here really is pushing the combustor to a more stable process.
All right. A question on the layout: can modules be stacked on top of each other?
Yeah, we're looking at we have a couple different configurations. We're looking at a plant, say, in New York City that is on the water, and we're basically going to bring in what we call the turbo house, and it's going to contain all the Turbophase modules and the cooling system, and there's going to be a fuel line and an air pipe hookup. And they can set it down right where they do their turbine maintenance. And when they need to do their turbine maintenance, the first thing they're going to do is they're going to pick this turbo house up and set it out in the parking lot, and then they can do their turbine maintenance. And we're also working with another plant where they literally don't have any spot. They're in a very, very confined space in New Jersey, right across the water from New York City, and we're proposing a parking garage. So the modules are up on a rack that's 15 feet off the ground, and there's 6 of them lined up, and it's basically a parking garage underneath. So we're putting it in the parking lot, but we're not losing the parking spot.
Okay. Another question: what are the emission levels at the exhaust for NOx and CO?
So this depending on what engine and what fuel, they vary wildly. But this recip engine, we picked the MTU Series 4000 engine because it's the most efficient, most reliable, and it's right in line with all the other big engine manufacturers' emissions. And matter of fact, the diesel version of this engine, which we have in our diesel Turbophase module, is the same engine that the U.S. Coast Guard uses in all their boats. So and they use that because of the reliability of the machine and the efficiency. But the emissions on the natural gas recip engine, for recip engines, they basically quote it in grams per horsepower hour. That's how the federal regulation subpart 4J defines the emissions regulations for the recip engines, natural gas. And this engine actually can operate and is operating here at Morris at basically half that level. So the emissions level is 1 gram per horsepower hour is the emissions rule, and we're operating at a half a gram per horsepower hour, which, when you look at it in terms of gas turbine emissions, is on the order of 40 ppm. And when you look at we're working with a number of customers that are in areas like California, for example, that have a 2 ppm requirement out the stack, and we can easily maintain the 2 ppm by putting our exhaust through the gas turbine, into the gas turbine stream and through the exhaust of the SCR of the gas turbine, and maintain the 2 ppm out the stack. And as well as when you look at actually how you operate the plant, since this incremental power is so much more fuel and emissions friendly than a duct burner, if you operate duct burners at all, you'll see a net reduction in emissions output from your plant. So that's kind of a high-level summary. The diesel system, most places where you could burn diesel, they're not that particular about emissions, but there is an SCR system that we offer for the diesel system if you want.
All right. Are the Turbophase module units running all the time? In other words, is the 60-second megawatt response based on valve position?
No, it's, start up the engine and inject the air. All happens in about 60 seconds. So we can go from a dead stop to, full air injection in 60 seconds.
Okay.
If we're running, it's more like 10 seconds. And as I kind of mentioned earlier, we're going after this regulation payment, which we're writing some algorithms right now that we're going to demonstrate, 1 to 2 second response time. So we're going to be we're also putting a small storage system with it that basically from a dead stop will get you power in 2 seconds at your plant. For places that have renewables and they're worried about, losing a plant on the grid, this power will be able to come onto the gas turbine in a couple seconds and stay on indefinitely.
Okay. The fuel values that are quoted for consumption and heat rates, are they using HHV or LHV basis?
Typically, we talk in LHV when we're talking efficiency, so they're in LHV.
Okay. Okay, go ahead.
I should point out, too, these first two modules, we're using I'll call it a not purpose-built compressor. So this compressor is not nearly as efficient as our production unit. And so if you look at the incremental efficiency of this Turbophase module on that 6-speed plant, we're going to be probably 600 to 800 points lower with our production module that we're building now.
All right. What about cold ambient? Is there a limit beyond generator load?
Well, a couple things. If you think about it, it depends on if you have a hot end or a cold end drive machine. And I don't want to get into the details on that, but let's just say on a hot end drive machine, you can actually go past what they quote as the shaft limit. out of your generator because it's actually not torquing the compressor shaft as much because of that 5% more power. 5% more air equals 10% more power. But on like a 7FA or so that's got the cold end drive machine, we're typically going to be limited to a shaft limit or a generator limit at the plant, and that's what we'll hit. That's what we're seeing with looking at maybe 50 different plants. That's typically what we're going to hit. So it will be shaft limited, and there's some temperature that you hit that on a 7FA it would be around 40 degrees Fahrenheit on a .03, where you'd have to start reducing the amount of air that you inject in the gas turbine from our system if you were putting 5% in. So you put 5% in at any temperature above, say, 40 degrees Fahrenheit and get that incremental power. But at 40 degrees, you have to start tapering it down, unless, like on a 7FA, they start opening the inlet bleed heat. And when they're opening the inlet bleed heat system, they start bleeding air out of the same port that we inject in. So we can put that air back in and basically keep you at shaft limit all the way down to really cold ambience. So it's a function of the gas turbine and what temperature you're operating and how many modules you have on it. So all that kind of plays into the economic calculation of how many modules to put on the gas turbine.
All right. A question, how much more efficient would a nominal 7FA be with Turbophase running in simple cycle?
It's about 2.5 to 3% plant heat rate improvement. So we'll take a high 9,000 heat rate, and your plant heat rate will come down by about 300 points.
All right. Is there an OEM maintenance penalty with Turbophase?
Kind of to the earlier question about OEMs endorsing our product, we've had a number of customers talk to the OEMs, and the answer we're getting back through our customers is no issue. So wouldn't expect them to implement one. It's almost the equivalent of putting a chiller on the front of the gas turbine. You wouldn't expect to, and it's not common, that you take a maintenance penalty for putting more air in your gas turbine.
All right. What about the question, why not use electric drives?
It's pretty simple. If we had an electric motor in our system generating 3 to 3.5 megawatts out of the 6B, we'd only be netting out 1.5 to the grid. And when you do the dollars per kW, it looks really, really bad. It's doubling the installed, dollars per kilowatt cost.
Okay. Can the system be used with a 7EA?
Yeah, we can put nominally 4 modules on a 7EA. If it's a hotter or high altitude, maybe 5 modules on a 7EA, and get between 15 and 20 megawatts.
All right. And what is the maintenance cost per megawatt hour for the Turbophase system?
We have a very detailed maintenance plan, and we actually offer the maintenance with our product if the customer is interested at about $3.50 per megawatt hour, which is pretty much in line with the gas turbine maintenance. And the reason it's so low for a recip engine is because we're making 2 to 2.5 times the power output of the nominal engine plate rating of our engine. So although the recip maintenance on a dollars per megawatt is more expensive for a recip engine, when you're making twice as much power and you're measuring it on a dollars per kilowatt hour basis, it reduces the number back down to something in line with a combined cycle power plant.
Okay, and I think we're getting about to our time limit, but I got one more here about how much more complicated or costly is the installation if you have a warm weather gas turbine module that does not have the inlet bleed heat piping.
It's very simple. We would just supply basically the equivalent of an inlet bleed heat manifold, and it's a very small cost adder.
Okay. So with that, I would like to thank you for the presentation. Both Bob and Bruce gave a lot of information about the Powerphase system. If you would like to view the program again, it will be archived on the Power website in the webinars section. Thanks to Powerphase for sponsoring today's event, and thank you all for attending. We hope you enjoyed the presentation and will benefit from today's program. If you had asked questions that weren't answered during the presentation, you can expect to possibly hear from Powerphase in an email to respond to those. So, to everyone, please have a great day.
Thanks, Aaron. And just one word is there's a bunch of questions that did come in that we didn't answer, and we'll answer them and post them on our website under our Q&A section on our website.
All right. Thanks, Bob.
Yep. Thank you, guys.